remember what domain and range is. You want to?
Yeah, like, this is domain. Is it like with the graph, like where you have like the, I don't know.
It's probably simpler than what you're trying to explain actually, based on mentioning the graph. The domain and range of functions are what?
Minimum and maximum.
No. They might include that, but both of them have minimums and maximums potentially in.
Like the maximum is minimum.
Well, yeah, in some sense, I'm not going to say no. In this case, it's as domain is so the domain is basically, in simple terms, all the x values. You have to state all the x values that work. We've already had those, haven't we? When we were talking about rational functions, why would I say some x values don't work? Because you can't divide by 0. So if there's an x value that does that, then it's not within the domain. Now, the reason why I can't say it's a minimum maximum, because an x value that doesn't work is not a minimum or a maximum, it's just an individual single value, right? But when we're doing functions that describe real-life contexts and things, we would have a domain that has limits at either end, potentially, because if we're describing something that makes no sense to go into negatives, then our domain would not include negatives. All right? So that's why I say it would give a valid result. So if I stuck an x value that ended up giving a negative result out, and that's not valid for the situation, we can't use it. In our rational functions, what we're saying is there are values that we're not allowed to put in because it will give us will make it so that we can't give a result, and that is because we can't divide by 0. So if we're asked to state the domain, we're basically being said, right, what x values am I able to put into that function? Does that make sense? What about range then? What do you think? Well, that is range within statistics. Minimum to maximum is the range. But if domain are all the x values that will give a valid result, all the y's, yeah? Okay. The possible y values. Could explain that better, I guess, but you get the idea, don't you? So basically, we're already aware that when we simplify rational functions, before we simplify or afterwards, we have to go back to the original and state the values that are not allowed, right? And that's how we're already stating the domain and the range. So there are certain things that we now will have, we need to take into consideration. Within rational functions, we've got these things called what are asymptotes?
Values of x or y that don't have
Not quite a full definition, but yes, we will. If we have an asymptote, let's say an asymptote is at x equals 3, it does mean that x equals 3 cannot go into the equation. But that's not actually entirely an asymptote. Yeah?
it's a line that can never be reached by the function, but it will come
Yeah, that's the difference. So an asymptote we can tend towards, all right? Cannot be used, but we can get infinitely close. All right? So in this case, I could use x equals 2.99999 forever, yeah? And that will be shown as in a graph where the line tends towards it, but never actually gets to that point. So if that's part of the domain, that's a value that I can put in. If it's part of the range, it's the result, what happens, and we will get infinitely close to that result, but never quite get there. So basically, that's what we're looking at in this topic, and how we can identify those. So we've got state the domain and range, draw a graph of the function, draw and label the asymptotes without a computer or graphical calculator. Although, if we all had graphical calculators, we would be able to use our graphical calculators to check that we're correct and use them when we get into DP to find them. So that's why we were encouraging you to get them. Right. So, any ideas? Let's have a look at y equals 4 divided by x. Steph?
Well, the asymptotes are x equals 0 and y equals 0.
Okay, so first off, I'm just going to put a little graph. I know I can have it in all 4 quadrants. So, the domain. What's the domain? Well, we're going to write this. I'm going to say x element of fancy R, but x cannot equal 0. Now, the reason why it's not just x is greater than 0, because x can be less than 0 as well. It can be negative, it just can't be 0. Do you know what this means? XER? X is an element of the set of real numbers. Yeah, that's what is an element of R for real numbers. Fancy R, so you know it's not just an R, it's the set of real numbers. Do we know how to? Do you all know why that is true? No? Well, if I try and put 0 into here, what do you get? Okay? 4 divided by 0. Right? If you put it into a calculator, graphical calculator, you will get an error or will get undefined. Okay? Because you can't divide by 0. So therefore, that's why x can't be 0. What does this bit mean? Well, it suggests that I can put any other value in. Does that make sense? Yeah? Alright. So what does that mean we do on our graph? Well, my asymptote, I'm going to put my dotted line at x equals 0. How does that look? It's the y-axis, isn't it? Yeah. The y-axis has equation x equals 0. Right. Now, Steph also mentioned the range, which is, he said y cannot equal 0. Could we write that y can be anything else? Well, I have, so yes. Why is that all right? Why is it not equal to 0? What's the problem with it?
Actually, if it was 4 over x equals 0, and divide 4 by
Yeah, so if we say this, guys, basically we're saying 4 divided by x. Well, if we try and make that equal 0, and then I tried to solve for x, what would I get?
You can rearrange that equation. 4 over 0 equals x.
Yeah. If I multiply through by x, I get 0 equals 4. Or if you do a complete, like Steph said, you could read it and say the logical statement would be 4 divided by 0 equals x, which can't happen. The other thing is, if you have a fraction where the numerator is an amount, well, a fraction is a division, right? So you can't divide something into pieces and get nothing. Yeah? If I have a cake, one cake, and I divide it into a million pieces, each one person might feel like they've got nothing, but actually if you all put it back together, you still got your cake, right? It's not nothing. So if you have so that would suggest that there are times when fractions can be equal to 0, which is when? 0 on the numerator. Yeah. So that is possible. But in this case, this is never going to happen, right? So that's why the y can't equal 0. Can y equal any other number? Yeah. Right. So we do have another asymptote though at y equals 0. Now, like I said, I know these are asymptotes and not just individual values. How do we know that? Well, do you remember what a rational function like 4 over x looks like? Just that? Well, let's work some values out. So if we put x equals 1 in, what will y equal? Okay? 4. If I put x equals 4 in, y will equal... Right, so let's just plot those. 1 and 4, 4 and 1. Right. Let's go for the other end. Let's do x equals -1. What will it be? -4. If I put x equals -4, we'll get y equals -1. So I will have 2 more points over here. Alright? So there's some just obvious ones at the moment, but what is happening? So we need a bit more. What would be another point to check? I've left some gaps. So should we do x equals 2 and x equals -2? What do you get? 2 and -2. So 2 and -2 would be there. Alright. We know that if I put x is 0, I can't do it. So what happens? So a lot of people would go, oh, I've got to join that with that. But that's not, we know that doesn't make sense, because if I just did that, a line is not a line, but an infinite number of points. Therefore, if the line does this, by the way, this is why I wanted to talk about it. If the line does that, we're basically saying that if I put a half in, I should get 2. If I put -1/2 in, I should get -2. Alright? Is that true? No. Let's have a look at what actually happens. So let's look at x equals 1/2 in. What do we get? 8. Y equals 8. So it doesn't do this. It actually goes up here. And what will do this? It will end up down here. Alright? So yes, like you're saying, Steph, it heads towards the asymptote. And that makes sense, because in a fraction, it's a division, right? So if the x gets closer to 0 in either direction, then the result will get bigger. Yeah? People think, oh, division is always smaller than 4, but that's not the case. So if x is a fraction itself, the number will be greater than 4 and it will just keep going up. So that will keep going up, and I can get infinitely close to 0, and therefore the amount will get infinitely big. And it's the same in the other direction. If I make x really, really big, so let's do x equals, what should we do, 50? Actually, let's, yeah. What would y be? 4 divided by 15 is 2 over 25 is 1 over. You want to do 1 over 2, is that right? Don't like that. Let's do 2 over 25. Okay? 2 25ths. How could you describe that as an amount? Really small. So as we head up to infinity on the x, this number is just going to get smaller and smaller and smaller, isn't it? And it will tend towards this line. So what we actually end up with these rational functions is, that's really badly done. We get a curve that does this and heads off, and then in this direction as well. We get a curve that does this and heads off in that direction. Be careful when you sketch these graphs so you don't actually cross that line, because even if you don't mean to, just because you're a hand-fisted, big, won't sharpen your pencil type of person, technically you just miss the point there. Yeah? You have to have it not cross the axis. Okay? So we've stated the domain, we've stated the range, we've got the equations of the asymptotes here, we've explained why, and we've got the shape of the graph. We have actually plotted some points so that I've got it. Okay, any questions on that? So, for you, got a negative one. You've got one where the x is multiplied by 4. And you've got a negative and where the x is multiplied by 3. So, have a go. What do you come up with? You'll probably find there's a pretty obvious similarity between all of them. The domain. X is allowed to be anything, but x is not allowed to equal 0. The range, y is allowed to be anything, but 0. So we're actually, for all of these, right, every single one of these, the asymptotes are in exactly the same place, which is great. Makes it nice and easy. So we do our axes, it seems a bit silly to do this, but it doesn't really show up. But here's one asymptote, here's the other asymptote. So, how does it look? Well, same thing. If I put x equals 1 in, what will y equal? Negative 8. So this time, right, if I make that there, that's negative 8. Then I know over negative 1, it will be positive 8. So, like that. And then we kind of get the idea that if that's positive 8, then we're going to have a negative 8 and a positive 8, and we're going to have another 2 points like that, yeah? So in this case, my line is going to be that. And that's fine. We're done. These are the main points. The 8s, they're the easy ones to find. Put them in. Now, if I were to put y equals negative 8 over x and y equals 4 over x on the same graph, you would see the effect of changing the The numerator. Well, slope, because we don't have a slope.
Yeah.
But this case, these points here would be here and here, right? Is that right? So that would be at 4, right?
Oh, no, that's for the two.
Yeah, sorry, even more. So,
That's only one line instead of
yeah,
two.
it would be here and here, wouldn't it? Here and here. So we would have 4 over x would look like this. So what happens when the numerator gets larger? Well, if you think about it, this one is times 2, and what do you apply as a transformation if you times by 2?
Stretch.
A stretch, and that's basically what's happened, isn't it? It's all stretched out. Yeah. So the smaller the numerator, the tighter the graph is into the origin. Yeah. The quicker it never gets to the asymptotes. If that makes any sense to you also. It will get towards the asymptote sooner, but never get there. But that's how you would compare. So you can see the difference here between a negative and a positive version, and you can see the difference between if I make the numerator larger. So actually, you should probably be able to do those two now. What's the impact of 4x and 3x, do you think? Are the shapes going to be exactly the same, or I'll let you figure those out? It's basically the same result. So we've got the length of time. Now, the reason why I wanted to look at this one today is because I want to check this aspect of it, which is time is inversely proportional to number of people working. All right? It takes 600 hours for 4 people. Model this situation with a rational function. Okay. So, do you remember your direct and inverse variation stuff? No? What does it mean? What inversely proportional means is that if I increase one, the other one decreases by the same proportion. So directly proportional means if I double one, I double the other. Inversely proportional means if I double one, I halve the other, which in this case makes sense, doesn't it? More people, less hours. All right? So how do I write that? So hopefully you would remember. So if we call this T, all right, and this N, maybe, we can write that, sorry, T, if you remember, I'm going to do it right from the start, is proportional to 1 over N. All right, that's the proportionality thing, which we then rewrite as T equals K over N, where we've got to solve for K. And how do we do that? Well, we've been given some information, 604. So when T equals 600, N equals 4, so we can chuck that in. Right, so 600 equals K divided by 4. It doesn't actually matter which way around you get this. You will just get a different value for K, and as long as you're consistent and work through that and solve for the right one, you're all good. So K is, times by 4 is 2,400. So the model I have, we must go from that, include K, and we then end up with T equals 2,400 over N. Right. Now, although it doesn't ask, what would the domain and range be? Sorry, what?
X is a
X? What?
T is a real number.
Which one's that?
Those are not real numbers.
Because I'm asking.
N is a real number.
Which one? Domain is
X. Whoa.
n. Right. We can say n is a real number. Okay, great. So if I can have 1.638 people working on my...
N is a whole number.
Ah, okay. N is not allowed to be any real number because n is the number of people. Okay, so n is an element of the natural numbers in this case.
What is that?
Or what?
It's a fancy n. N with a double line.
What is that New York thing? I'm mad.
Alright. Next time you lot draw stuff, you know what's funny.
There we go.
So n is a natural number. Do we need to state anything else now? Okay, n can't
Well-
equal that. Doesn't make sense.
Well,
does
it
it?
could
Yeah.
equal
Well, actually,
zero,
here's
you
the
just
question:
don't have
is 0 part of natural numbers?
You could technically you could have 0 because if no one works on it, then you just don't have a
Because you
bullet.
can't divide by 0.
Divide by 0.
But
Because it would take an
But
infinite amount of time, or it'd be an undefined time. The question that I'm asking at the moment, I could put integers. Integers are negatives. You told me natural numbers, which I'm very happy to write natural. Do I need to put anything else?
N
Well,
has
would
to be
it-
greater than 0.
Do I need to put n is greater than 0?
0.
What's the first natural number?
1.
Okay. There is this discussion whether 0 is an integer or not. But I think we know that the natural numbers do not include 0, because when you naturally count things, the first number you use is 1.
1.
Alright? Because if I said, oh, excuse me, how many sheep are out there?
0.
There aren't any. I don't use 0. There aren't any sheep. Oh, there's 1 sheep. 2 sheep. No, careful, I'm going to fall asleep. Alright? So the domain, we could say natural numbers. I don't need to put that. The range is t.
Could be any,
Any natural.
well, I guess it can be negative, but it could be.
Could we say t is allowed to be any real number?
Well,
Positive.
Because we're going to get 2,400. We are going to get decimals, right? So that's right. But t must be not equal to 0 this time, because t must be positive. So we're going to say t must be greater than 0 this time. So we're going to say it slightly differently. So this is an example of, in a contextual question, the domain and range, although this is a nice simple y equals something over x, the domain and the range, we need to be a little bit more descriptive with it. Can I draw a line? What's a line? Am I allowed an infinite number of points? Technically, I'm not allowed to draw a line in this case. I'm only allowed points when there's a natural number. If n is not a natural number, I'm not allowed to put a point. Therefore, shouldn't be drawing a line for this graph. I should just have points, all right, at the relevant stages. And that's why we say it's not a line. Awesome. Have a good day.